So this is joint work with some colleagues from Madrid. And what do we do basically? Well, we take a web service that's communicating using JSON, and we want to be able to test it using QuickCheck. So this is going to be an introduction to the techniques, the languages we use to accomplish this. Okay? Please feel free to interrupt me at any point in time, because it's more fun, a little bit more interactive presentation. Okay? So basically, the content. So for those unfamiliar with JSON, I don't think there are many anymore, but I'll start with one slide just introducing the language. And probably not so many of you know what JSON schema is. Anybody know about that? No? Well, some. It's a proposal for a language for defining types over JSON. So something similar to XML schema for XML data, right? So you can describe the type of JSON data that you communicate. But also, interestingly, there is a part in JSON schema that is similar to, if you will, WSDL. That is a language mechanism for talking about how you interact with a web service. What URIs do you use? What kind of data do you send? What operations are there? And things like that. So we'll use both those features to accomplish testing. Okay? So technically, what do we do? Well, there are two things we do. We take a schema, a JSON schema, which defines type, and we translate that schema to a QuickCheck generator. And using that QuickCheck generator, we can then generate an unbounded number of data for test data. Secondly, we want to test web services. How do we do that? Well, we provide one generic QuickCheck state machine to do that. And there are also mechanisms for how to tailor that QuickCheck state machine to do what you really want to do when you test your web service. Okay. So this is going to be pretty example-based, and you're going to see a lot of JSON and very little Erlang. I apologize for that. Okay. So what is JSON? Well, it's a very simple readable data format. You have basic types like integers, strings, whatever. And you have two complex types. There are arrays, which can contain JSON data, JSON values of different types. And there are objects, which are basically just a collection of key value pairs. So here we have a key first name with a value John, etc. So they're very simple things. Okay? So JSON schemas. Well, this is a way of describing types for JSON values, and a JSON schema is itself represented in JSON. Unfortunately, as you can see from the title, these are very wordy types. They are a little bit too long to really be nice. So, in my opinion, a better language would be better. But okay, let's use that for now. Okay. So here's the object we saw on the last page. How can you describe that? Well, here's the description as a JSON schema. This object is of object. We require the following set of keys. First name should be there, last name should be there, age should be there. What are the properties of the values of these keys? Well, the value of first name should be a string, the value of last name should be a string as well, and the age should be an integer. So it's fairly straightforward. Okay? So, interesting features, of course, a little bit like XML. There are many things that there are actually many type of different values that can match this type, right? So for instance, this one was of the type, but you can also add more keys. You can have a garbage key here, JFPSL, etc. This is also that this object will also match the previous definition. You can add other keys as well. And of course, when we do test generation, we want to be able to generate such additional key values as well. So you can restrict in JSON schema. You can say restrict, oh, we just want these keys, and you can add some additional statement ends to restrict your values to only the keys that you mentioned. Okay, so there is a way to do it, but by default, well, you can have extra things in there. That's it. Okay. So here's a more precise type. We have the same first name, last name, age, but now we also want to say, well, what is a first name? Well, it should probably be on this format, so we give a regular expression and say it should definitely begin with a capital letter, and then there should be some lowercase letters. Okay? And the same for last name. age, let's be optimistic, age is between 0 and 150. So let's hope this comes true. Okay? So, well, we have done this, the task of translating such schemas into QuickCheck generators, and what we have seen so far, it's pretty straightforward. I mean, you have already good QuickCheck generator for integers with minimum and maximum values. There's no complication. Strings are fine. Regular expression add a little bit complexity, but not really that much. Okay, so this is handleable. Constructs that generate more problem. Here's an example. So in JSON schema, we can have both what I call global and local constraints. So the same person object, whatever. Let's refine what we mean by our first name. So our first name is a string. It matches this regular expression. So this is a local constraint. But we also say, sort of outside this regular expression, we have a global constraint saying that the minimal length of this first name should be 20 and the maximum length should be 56. So how does one generate data for that, test data for that? Well, ideally, one should probably combine these global and local constraints, have a dedicated constraints rule, I don't know what. What we do in practice for now is we do a really stupid translation. So we generate using these local constraints, and then we generate a set of values, and we throw away the values that don't match these, the global constraints. And of course, this is a well-known problem in test data generation, that this can lead to inefficiency. For instance, in this case, probably it's pretty probable that the names you generate are going to be rather short, so you're going to throw away a lot of names. This is going to take a lot of time to generate data. So it's not ideal, but it's what we do for now. This is one complication. Another complication is that in JSON schemas as well, you have a pretty expressive type language. So you have combinators, you have conjunction. You can take two schemas and say, oh, I want a type that is the conjunction of two schemas. Okay? And if you will, you also have schema disjunction. That's okay. You have schema negation. Let's see an example. So here is a schema. Here's a type definition. What does it say? I begin with not. What not? Well, the negation of an integer with a maximum value of 100. Okay. So which values match this type with this schema? So let's think. So anything that is not an integer, right, would be okay. And given an integer is okay if the maximum value is greater than 100. So this is not a very constructive definition, and we want a constructive definition to be able to generate test data. So problem again, the same kind of problem as last time. So well, we can do an approximation for this again, which is not ideal. It's going to be stupid. It's going to be inefficient. It's going to be bad in many cases. Okay, let's do it. So the stupid idea is to let's generate data using the most general schema available, which is the left brace, right brace. This matches any value. Let's then check, well, we generate values, and let's throw away values that are not validated, that doesn't conform to doesn't conform to this type. Okay. So again, we risk the problem of throwing away lots of data. And for doing that, we need a validation tool. We don't only need a tool for generating data, but we also need a validator for JSON schemas and JSON values, and we use the JSON tool to do that. Okay? This is doable, but possibly inefficient. Out of curiosity, just to familiarize you a little bit more with JSON schema, here's another feature. We can have references, so you can have recursive definition. Here's a definition of the piano numbers, and using that, you can, the QuickCheck generator that you get out, you can generate values like 0, successor of 0, successor of 0, etc. So quite a lot of expressive power. So that was the first part. We know how to generate test data. Now we want to talk web services that communicate using JSON. Well, there is actually, as I said in the beginning, there is actually a feature for adding more information in that JSON schema about web services as well. How do you access a web service? How do you communicate it? Let's look at an example. So The example we're going to use is a very simple web service that's used for storing questions. So a question, what is pi, for instance, could be a question, a statement. And each question should come with a question identifier. Okay? And there is a simple web service that we use that we design ourselves to do testing. Okay, around that. So questions have a statement and a question identifier, which is an integer. Okay, now one can start adding links to JSON schemas. A link is essentially, if you will, an URI endpoint talking about how you can access a web service. Okay, so let's extend the previous definition, the question type that we saw. Let's extend it. We can add links here. So here's one link. So it looks very, very operational. We say, oh, here's the address, if you will, how to access it. Let's, for the test purpose, we use a local address. And we add a /q to it. Okay. What is the method to accessing this, to interacting with this link? Well, it's a GET. So we're talking about RESTful web services generally. Okay. And if you do a GET on this address, what do you get back? The target schema, so this return type. It's an array where the items in the array are all going to be questions themselves. So if we access this URI, we get back questions. Okay, so you have a little bit more information now. You can work with this actually to interact with the web service. Okay. For the purpose of the talk, let's also introduce answers. So an answer is an answer to a question, mentions the question identifier, and has an answer which is a string, of course. So how do we add an answer? That's another example. We have another address, /a at the end, because we have the RESTful stuff. The method here is not get, but post. So we post an answer. What is the argument for an answer that we have to supply when we do a post? Well, here's the schema. So we should supply an answer. This is, of course, the thing inside here, an integer, a string. Okay? Now what do we get back? We get back something that is an answer. Right? So these are, if you can look at the addresses, these are all static addresses. There is nothing variable here. We have /q, we have /a. This is not very interesting, perhaps. One can also add what I like to call dynamic links to such descriptions. So here's another link in answer as well. We say that, oh, we can actually, given that we have an answer object, okay, we can actually find the corresponding question object as well. And this is how we do it. We use this address, /q, where we plug in, so this is syntax for plugging in the value of QID in the object. Okay? And this is get again, and what we get back, we get back a question, of course. So given an answer with a QID, we can find the corresponding question object using the above. Okay? Okay, so links. They are actually pretty useful then. And we use the link concept to design a state machine that systematically explore all links that are documented in the schema. So you can yourself control, by adding more or less links to the schema, you can control what the state machine is going to do. Okay? So we provide a generic state machine JSON, or whatever it's called currently. The state of this state machine, for those that know QuickCheck state machine, it's in some sense no more than or no less the set of known links, or the URIs, whatever you want to call them. Okay, so links. And how do we explore? Initially we begin with the static links, the one that doesn't require us to have any objects. And then using those static links we'll encounter new objects, and we will be able to follow dynamic links as well, etc. And we do this process continuously. Okay? So what do we do for a link? Well, if a link corresponds, following a link corresponds to doing a web service call. And what do we check? Well, we check by default that the return result, of course, should match its definition in the JSON schema. For instance, that the target schema, if we follow this question link here, we really get back a question that the data is not that format, so we have to validate the data. Etc. We also check that the return product is okay, of course. Arguments to call, well, we have QuickCheck, so we can generate the arguments to call automatically from the JSON schema. Okay. So for instance, here we saw an example. We are doing a post, we should send along an answer. Well, we can generate it automatically and do something like this. Okay. As a technical comment for those that don't know state machine, we do not actually use the classical EQC statement library to do that. We actually use a new library that Hans or Thomas can talk more about. That is dynamic. So we actually combine the phase of test generation and test execution in the same place. And that turns out to be a little bit more easy to do actually for these kind of problems. It's a nice library. I recommend it. Okay, so we can run the thing now. We have a direct state machine. We have our own syntax for doing that. Let's call it. We supply as an argument the JSON schemas that we use as a starting point. So this question may be answered here as well. Okay. So QuickCheck starts and very quickly it finds an error. Post condition error for the HTTP call. We try to add an answer probably using post. Here was the body. QID 18. The answer was blah blah blah. Some garbage thing. Okay. And HTTP responded with result 409. We expected the result of 200. So it failed. So what went wrong?
There was no question.
There was no question. There is no question with that question identifier. And depending on the web service, some web services would add it anyway. Some less pure RESTful web services would create an error here as this web service does. So it depends a little bit on your web service what it does in that situation. Okay, so adding an answer to a non-existing question. So clearly, we're not getting very far with many web services if we just do this generic following links. We need to have a little bit more intelligence in how we generate these values. Okay? So what we do, we want to add specific functionality to the generic state machine. So in this concrete case, let's look at the concrete case. What should we do? Well, one thing we could do, we could start remembering the question identifiers that we do generate when we add a question to the system. Well, we're going to remember it. So technically, in the next state function, we should probably add the QID as separated to the state, machine state. And when we do operation that references that QID, for instance, this adding an answer, we probably have to check in the post condition whether the QID we generate is already existing or not, and be in that way to be able to handle errors, to expect errors. And it turns out we have already prepared this generate state machine to be refined in such a manner. So actually there was an argument which you didn't see here. We can supply a model here which refines the generic state machine model n. Okay? So this module should supply more or less the same function. It doesn't have to supply all the functions of the state machine, but it can supply some of them, the ones that are interesting. For instance, we can supply next state. And this is going to be called now with 4 arguments instead of the usual 3. So the usual arguments is the state, in which the state machine is in, the result of the call, and the call itself. So a symbolic representation of what the operation tries to do. Okay? But we also send along actually a function here, which is a representation. So this is a call to the new specific state machine, and to that we send along the function representing the generic state machine, what it does for next state. Okay? And actually, the code in next state, in our next state, can choose to call this one generic next state if we want to do that. So this is how, in some sense, we approach the adding a specific functionality. There are many ways of doing it. One thing is refactoring your code, then you try to change things. But we wanted to do something a little bit more, to have state machine, the specific state machine as an independent entity. Okay? So we do refinement in this way. Like that. Let's see an example. So here's an example of the next state for this very simple web service. So what was the problem? Well, if the call is add question, so here there's a lot of syntax here, but let's forget about it. So basically links have a name as well, so we look at the name of the link. So if the link we followed was an add question link, well, let's actually extract from the result body the QID that was used. So we extract the QID. Let's extract from the state so we have stored in the state the previous QIDs that were created. Let's extract them. And let's create a new state. So here we create a new state saying that, well, the new state is going to be QID, a list containing QID and the old QIDs. Okay, so we add QID to the state. Okay? And we call super again. Super is, of course, the generic function here, so which does what we normally should do for next state. Okay? And if it's not an add question, well, we call it just super. So this is looking a little bit like object-oriented programming, a little bit scary, but sometimes this is a good metaphor. And to me, this is an example where it's a good metaphor. So what does super really do in this case? What does the next statement do? Well, it follows the links. It remembers the links that you follow. That's really crucial. Remember the links. You wouldn't want to forget. Okay? And the same, you can handle post condition in the same way. And it seems to be a pretty okay way to do things. Okay? So let me wrap up. Is this a ready tool? Well, as the previous speaker has said, our tool also not really completed. It's not really useful for heavy-duty work, perhaps, but it's already proving a little bit useful, at least for us. So what is missing? Well, I touched upon the problem of data generation. This is always a problem when you're doing project-based testing, in my opinion. We have to do better test generation. We have to handle better cases like mixing global and local constraints, or at least giving the possibility for a user to override the default generated generators. Another thing, if we're looking at RESTful web services, there are different classes of RESTful services. There are these very pure RESTful services, and if you have a very pure RESTful services, you actually know quite a lot more about how it should behave. So if you specify, well, my web service is purely RESTful, then you can do more tests. And we haven't really implemented those yet. Another, in my opinion, class of web services are what I call RESTful hierarchical web services, where the URIs are organized in a very hierarchical manner. And there are different styles there. And if you know that your web service should be hierarchical in this manner, you can do quite a lot more tests. Another comment, at least to me, if you want to do this kind of, if you will, do QuickCheck state machines for other kind of applications, well, maybe a good way of doing it is actually to refine your state machines in this manner. Design a generic state machine that doesn't do completely what you want to do, and then add some refinements to it in this manner. And to me, it seems like an okay technology. Okay. Thank you.
Break for lunch now. There aren't any questions here?
Can you go back to the example in the schema with the links?
With the?
Where you specify the links?
Yeah.
Yeah, any of those. Go forward a couple.
So this one, for instance, or?
There's one where you specify like the HTTP verb, and you specify the type of operation. One more maybe? Yeah. For instance, something like this. So in terms of the REST stuff, I think like if you could assume the web service followed like the principles of REST, it'd be interesting to have you not specified as links and say rather these are related resources, and then you could automatically generate posts versus gets, or puts versus gets, and patches and calls like that, and know automatically how to operate over those resources.
Yes, but it's yes.
I also think that there might be something interesting with some of that you could do with some of the return codes. For instance, if you were trying to add an answer for a particular question, you could automatically know that you need to add the question without having to encode it in the state machine by using something like a precondition valve or some other HTTP response.
The problem is that we are living in a very impure world.
Yeah. Well, you know, I'm like,
we want to do these things, but very few really pure web services.
Yeah. Well, I'm in the Basho camp with the web machine guys, right? So yeah, obviously my opinion is very biased.
And it's interesting. It's really interesting. And
we'll call home and set these
Cool. Thank you very much.
Thank you.
Do we have any more questions?